Hello, here will be our first lecture of our CSCI 430 operating system. And it's like the first week video, so we kind of like go through some like keywords of some like terms, including the computer system, and there's some like interrelationship. Okay, so that's what we cover, some like certain hardware name. Okay, and then some register. And one thing we will cover today is the interrupt. Okay, so this will be cover what we go through for today. So when we look at the top view of our the hardware, so including the CPU. So if you know the CPU, actually inside CPU you will see lots of different register. Okay, and some other parts. Okay, so once if you see the PC, later even the exercise. Okay, because we are using the C purpose to simulate, okay, how the CPU control or manage certain tasks. Okay, certain stage. So we have one is called a program counter. So why not in this moment you don't have to really worry about it. Okay, what do they mean? Okay, what they are doing, but you at least you need to have a like an idea, know what's in the CPU. Okay, and later we will in the later lecture, so we'll cover like what's the PC okay using for, and then what's the IR, the instruction register doing. Okay, and of course we have some exercise. Okay, and also we have the MAR, the memory address register, and then the MBR, so we have the memory buffer register. Okay, and of course we do have some IO AR, the address register, and also the IO BR, the input output buffer register. So this will be in the CPU. And we also have counting the execution unit. Okay. And next part we heard a lot about is the main memory. Okay, so when we say like how many gigabytes of RAM, okay, so will be main memory. So it's the end of the name we use. Okay, if in the lecture or sometime when you see on the exercise on the lab, okay, assignment, some question, you say, okay, what's main memory? Actually, it's the RAM. Okay, and from the RAM we have certain we have the address. Okay, so maybe once you load your OS, okay, so there's a part of a memory, so will be being occupied by the operating system, and then certain application like necessary and for supporting your OS, so they will also load to the main memory. Okay, so in the slightly about the history of it, long time ago when you see the like 32-bit, or if you see the folder, like especially right here we use the example is Windows. Okay, if you have no idea about like Windows system, then try to find some opportunity, look, check the folder. So the C file and then program file under it. So we see one is called the x86. Okay, another one 64. Okay, 86 is representing the 32-bit. Okay, all the applications. And the main differences between 32-bit and 64-bit is the size of the RAM. Okay, so it's like it's a really long time ago. Nowadays, you know the RAM you're using more than maybe 16 gigabyte or 32 gigabyte or more than 64. Okay, so 128. Okay, but if we're using 32-bit system, okay, the maximum support of a memory is 4 gigabyte. Okay, so even you put 4 gigabyte, like increase to 8 gigabyte, your system, your operating system cannot utilize the like more than 4 gigabyte. So you can't wasting it. Okay, so just like you have a lot of memory, but your system only can recognize from the 0 location to 4 gigabyte, and that's it. If you have more address, they cannot use it. Okay, so it's kind of erased. Okay, and then in the memory, so including different section. Okay, so maybe sometimes they will storing the instruction, sometimes storing data, some like programs. Okay, so they put on it, and of course, next part is the I/O. Okay, so for the I/O modules, and also it comes with the buffer, okay, for the input. So those I/O, if you know some examples, including like your keyboard, your mouse, okay, and maybe you have the printer, okay. So all these can be your OLED monitor. So they can be your I/O system input output. Okay, so that's why we have the input output address register, and also we have including the buffer. Okay, so why we need to have a buffer right here? We don't have. I'm not explaining the detail. If later you know, but just like knowing buffer is helping us like to keeping certain input. Okay, so we are not reading. Just imagining if we are reading a word, but without a buffer, you need to read the character one by one, letter by letter. But um, if we're using buffer, then at least we can save a sentence or a word. Okay, then save it to CPU. So it will help the performance. Okay, so here's a kind of idea like where's the hardware inside your computer, and then when we learning operating system. So this OS is like operating all this, okay, managing the CPU, main memory, I/O. Of course, later we will talk about the second storage. Okay, of course, that means your hard drive. Okay, so here's the top view of it. Getting, and we talk about the processor, that means the CPU. Okay, so it what's the function? So it can control the operation of the computer, okay, performs like numeral calculation. So mainly it's numeral calculation, okay. And every time we're reading the instruction, they adding like move. We always say the assembly language because I know some of you already learned the assembly language. So every instruction, so always like it's the numeral calculation, and also it performs the data processing function. So this one is the I/O. So we say the data process. Okay. So if we have the keyboard input, okay, so the processor will take care of it. Also including some general purpose. Okay, so maybe some system can handle some special purpose like processor. Okay, so it's more than that. But most of the time we just like, look at the general case. Okay, so it's the CPU, the processor. So whenever you see the name, okay, processor or CPU, then they mean the same one. Okay, and next one is the main memory. That means we talk about the RAM. Okay, so here's the characteristic of RAM is a volatile. So what's volatile? Volatile is that it lost all the um content once lost the power. Okay, that means no electricity. Um, then we cannot save it. Okay, so that's why once you reboot your computer, shut down, and then um start your computer. So everything they start as a new scratch like that. Okay. So it's a volatile. Okay. And also the contents of the memory. So it's lost. So when the computer is shut down, so that's what it means. And it also refers to some like real memory or primary memory. So we talk about it because later we will introduce and the one's called a virtual memory. Okay. So it is using the part of your hard drive, okay, or the second storage. So that one is using if your main memory is not enough, then we're using the virtual memory. So you see the keyword real memory. Okay, so when we talk about that, will be our main memory. Okay, and next one, when you look at the pictures of the I/O modules, so it moves the data, okay, between the computer and external environment. Okay, so that is, and then we have different variety of devices, okay, and we can say as a block, and we talk about some like characters, okay, and also we have some special bus, okay, interface. So they may be like some system bus, so including the USB, okay. So if you go back to the picture, right here, we're going to talk about the system bus. Okay, so here's another term we will say a lot. The system bus is the connection between the CPU, main memory, I/O, or like everything on the motherboard. Okay, so they're being connected. So they are the imagine they can be the you can think in this a row or is a bridge. Okay, so therefore connect them together. So it's the system bus. And it provides for the communication among processor, memory, and I/O modules. Okay, and sometimes we have terms that talk about um, the performance of the system bus is the bandwidth. Okay, the bandwidth. Just imagine if the row with like one link, two links, okay, or three links, okay, then it will affect the speed of transmission. Okay, so here's the idea of system bus. But this is not a main concept of it. Okay, and later, after we know all the keywords related to like processor, main memory, I/O modules, and the next one we need to know is the instruction execution. Okay, so because we talk about like processor, we execute the instruction, right? So the next part we need to know is the fetch execute cycle. Okay, of course, start with the most easy and basic one. So the basic instruction cycle, we have the starting point, okay, and hot, that means end, okay. So if we are executing the basic one, we try to fetch the next instruction, okay, and execute that instruction, okay. And in this execute stage, we say, okay, execute stage, okay, maybe we will go back, okay, and then let's loop and then fetch state, go back to fetch next instruction, execute it, fetch next one, and then once we finish the execution, fetch the next one, and then execute. So it's a loop until we finish the whole program. So it's the basic instruction cycle. Okay, that's what you need to know. And right here, so when we try to fetch, okay, later, after finish, we will have more work to related to the fetch cycle, and the processor will fetch the instruction from the memory. If you remember, we have a graph right here in the main memory. Okay, so we have certain instruction. So we will fetch it, okay, send it right here. Of course, we have more including the PCIR, all the register to save. Okay, which one should be the next one? Okay, we'll go through more details. But in this moment, you see, okay, right here. So when we fetch, so the first keyword that comes out is the PC, the program counter. Okay, so the program counter holds the address of the instruction to be fetched next. Okay, so the PC is increment after the each fetch. So you will need to know the keyword address. Okay, so because we are saving the PC is keeping the address of the instruction. That means the address of the instruction will be stored in the PC. Okay, so the PC is checking, okay, so what's the instruction? And next time when I finish the fetch, then we'll press one, then we'll go to the next instruction. Okay, here's the location of the main memory. So it's the address, okay, but not the value, okay? So careful of this part. And then we move on. So for those different type of instructions, we have different categories, okay? So when we fetch the instruction, so they will load into instruction register. Okay, those instructions, so PC and IR. So the IR is the instruction register. Okay, and in general, so right here we have four categories of instruction. One is the processor memory. Okay, so it's related to the data, so maybe transferred from the processor to memory or from memory to processor. Okay, so it's one of it. And next one, processor I/O. The data may be transferred to or from the peripheral I/O device. Okay, so it's the processor I/O. So this one, and then the third one is the data processing. Okay, so the process may perform some arithmetic logic operation on the data. Okay, so here involve the other hardware part. Okay, this one is the data itself. Okay, some arithmetic or logic operation. Okay, and then we have the execution control. This is the last one. So there's an instruction, So may like specify that maybe the sequence of the execution be altered. So right here would be the execution control. The first two just remember, okay. So remember to the hardware. So of course we need our processor CPU, and we will work with memory. Okay. So just transfer data between processor and memory. Second one, processor with I/O. Okay. And last part is the data processing itself. Okay, so that means we are working on the CPU, the processor. Okay, and also the execution control. So it's an instruction. So may specify. Okay, what's the sequence of execution like this? Okay, maybe change. Okay, here's the instruction being saved. So it will be IR. Okay, store. And in the IR, just remember, so all these like fetch instruction, they're load into the instruction. Okay, so be careful. What's PC? What's the IR? These are two words, right? And the processor interrupt. Okay, so the instruction, okay, interpret the instruction and then perform required action. So what's the following action? Remember, so processor to memory or memory to processor, process to I/O back to processor. Okay, data processing and execution control. So we'll be right here. So we put it in the and later we do have more example you see, but so far right here. So the characteristics, so the hypothetical machine right here. Let's say we have the 16-bit okay instruction. Okay, here format. And, we have 4-bit opcode. You see because we start from 0 right here. So the first 4-bit 0, 1, 2, 3. Okay. So will be the opcode. Okay, and then for the rest it will be the address. Okay. So and another one if for the integer, okay, so maybe the first bit, okay, is the sign, okay, and then the rest of it will be the value, okay, magnitude right here, and the program pointer, if you still remember, is the saving the address of instruction, right? So what's the address of it? Okay, and then after we load the PC, then we know, okay, and then the IR will save the instruction in it. Okay, so it's an instruction being executed, and we do have a accumulator AC, if you another term is called AC. So it's a temporary storage. Okay, so we save it, and the C right here you see is the internal CPU register. Okay, right here. So you can see. And if you look at the example right here, so let's say we have serial one, we say it's low. Okay, low AC from the memory. Serial 1, 0 is store the AC to the memory. And then 0, 1, 0, 1 add AC from memory. Okay, so here will be the just the you see the partial list of the opcodes over here. So it's a 4-digit, right? So that's why 0 to 3 opcode 4-digit code. So 1 is low, 2 is store. Okay. Then what's this one? The number. If you have no idea, then you need to know how to calculate. So because the first one represents 1, second one is 2, 4, 6, right? So right here it would be like 4 plus 1. So it would be 5. Okay, that means the number 5 would be add the AC from memory. Okay, so all this opcode. So we the OS already defined what's the opcode right for doing certain execution. So we'll know. In this moment, you just need to know. Okay, we have certain opcodes for the internal like CPU registered like taking instruction execution like this. Okay, and when we're learning the operating system. Okay, so we do handle a lot like different from like primary decimal. Okay, has decimal numbers. Okay, so you're welcome to looking for more details. As a like actually next week, prepare to kind of like release the first easy assignment. Okay, so it's also related to some binary. Also later we are not really only focus Windows, so I'll give you some like command like instruction. So helping to check. Okay. But this one will be later. Okay. And just like let you know earlier about the next assignment. here back to our lecture. Okay, here's the example of the program execution. On the left side, okay, and will be the memory. Okay, and we start from 300. Okay, part of it until like 941 right here. And we have the PC ACIR. Okay, there's like what the register memory. Okay, and if you remember in the beginning, I talked about when I look at the top view of our hardware. Okay, we say when we load in the memory, including the OS itself or other application, other software. So even memory start from zero, maybe some instruction data, they're not exactly like stored in sequence, okay, on the memory. And also if later in the later part when we talk about the memory, okay, like the paging somehow, okay, so you know the address is not like in sequence, okay, so they're jumping. But for the program counter, I will let you the first condition. Let's say we have the PC 3, okay. If you remember what's the instruction, um, if you still right here only 2, but we don't have 3, so just like letting you know, let's say if we had the like PC and then we have the 1940 right here. If you remember what's the 1 and what's the 940, okay, so it's the IR instruction. And 1 which are, and then what's the 940 is the location 003, we get an array, so the accumulator, so we save the value. Okay, and when we fetch, if you remember the program counter, we pass 1. So in the next execute stage, then we pass 1. Okay, and then AC will be 003. If you can follow it, and then we move to step 3 because the next program counter is 5. The program counter 5, opcode 5, and then next address is 002 49 5941. So 5 is the opcode address, 941 is the memory address, right? So we can load it. If you remember, what's the opcode 5? Just come back from here. Let's say 4 plus 1, 5, add AC from the memory. Okay, add to AC from the memory. So we just add to AC. Okay, and so 2, add to AC, 2 plus 5. Okay, and then we will update the AC. And also, after the first cycle, the PC counter, okay, the counter plus 1. So it's a 302, okay, 302. And next stage after we in the execution stage, like completed, okay, so we'll be fine. The next one we fetch 302, okay, 302, opcode 2, and then go address 941, okay, opcode 2, 941. So what's the opcode? 2 to store AC to memory. Okay, store AC to memory. So store. So what's the address? We have to check it out. So we store it back to address 941. So we put it back right here. So you see we update 2 to 5. So here will be the program execution stage. So if you have the idea, so here's the basic mile. We do have a exercise, a more detailed exercise, and it will put it as an assignment too, like for you to work on it. Okay, and quickly so far we go through the first part. Okay, so here's the review question. So you can look at it. Okay, so what is the if there what's the category? This like hypothetical like machine instruction. They're kind of like we calling your assembly language low jump. Okay, multi. Okay, so what they're doing. So what's the category doing? So you can think about that. Okay, so low. If we talk about low, it's like from where to where. Okay, so probably should be from memory to our processor. Okay, maybe jump. Okay, so from certain location to any location. Okay, and then we are multi. Okay, timesheet. Okay, calculation, processing. Okay, so you can try to match with the categories right here. So you match like loading from where to where. Okay, so does it including I/O, data processing, some like arithmetic logical operation. Okay, and then specific some sequence, like if they're alter, okay, jump. If you talk about jump, so we'll like the sequence, okay. So right here, then I think it's pretty straightforward. What's the answer right here? And then what's the two basic steps? Like use the by some like typical processor in the instruction. Okay, so I think this one is like what we talking for the last um previous several slides. So just like recall it. So I think it's a really strict um answer. Okay, so I'm not going to say it. Okay, and also we have like more question. Let's say with the pseudocode. Okay, like here, show the program execution. Like what's the 300 301 adding and then 302 dot AC. Okay, like this. What's the AC right now? So basically, and if you're interested, you're welcome to look at it. Of course, we have more exercise for you as an assignment so you can practice and do it. Okay, and here will be the next part we will cover in the lecture is the interrupt. Okay, so interrupt, we need to understand the concept. What's the interrupts and how and why a processor use interrupt. Okay, so in the beginning, we have some common classes like of the interrupt. One is program. So what's a program? So it's generated by some condition, okay, occur as a result of an instruction execution. So when we execute certain instruction, then there's a result. We maybe generate certain condition. So let's say arithmetic overflow, division by zero right here. So it attempt to execute an illegal, so we make illegal machine instruction, okay, and refer to the outside users like allow memory space. So here's the thing. So okay, so if we have certain interrupt, and then it's like caused by program. If you are writing program, if you see the alert or error pops out, say divide division of by zero like that, okay, or sometimes when it's overflow, is that if you are really too large number adding together or minus, then it causes sometimes with the overflow, okay. And then timer, so that timer will be generated by the timer that within the processor, actually in the processor. But this moment you maybe don't know like what's which part of timer, but you just need to know, okay, right here was one class of interrupt is caused by the timer. So this allows the OS to perform certain function on the regular basis, okay, right here. And another one interrupts from the IO, okay, IO controller. It is a signal normal completion of the operation or like signal a variety of error condition. So it's an interrupt from IO. And the hardware failure. Okay, so if we have some like failure, like power failure or memory practice area, so it causes a hardware. Okay, so we have four common kinds of interrupts. Okay, you need to know. And right here is the some flow control without interrupt. Okay, so here's a compare. If we have no interrupt, first we have program, right? So in the first state, okay, getting, and then we have some write. No, then we will jump to the IO program. Okay, IO, and then getting input. Okay, so maybe we are waiting for a certain commands, waiting for it until it finish, then we go back to run, and then execution and things. And if we're another wait, we also have to go back to IO and wait until the last moment. And then once you end, we go back. Okay, so here's the no interrupt. Okay, because the main flow is right here. If we have certain IO, we have interrupt. Without the interrupt, we have write to IO. Then we'll go there and wait until complete and come back. Original, okay. Right here, and then keep going. And if we do have interrupt, so we have the short IO wait. Okay, so right here, let's say we have the first part. We're waiting, we have a write, we getting a short input. Okay, once you finish, so finish the interrupt, we'll go back. Okay, keep on execute. But in case we have another interrupt, okay, handle it happen. Okay, so you will see maybe this part. Okay, so it will going to interrupt only in middle of part two, right? So go to execute and go back. Okay, when we have a write, we still go back to IO. Let's say complete and keep on execute and then waiting for another interrupt. Okay, interrupt, and once it's complete, we will go back to it. Okay, so here's the differences. Okay, if we the flow without interrupt, we always waiting complete until getting input. Okay, If you're writing some low-level language, when you pop out like waiting for input, then you cannot do anything, okay, until it complete or we reset the input or complete the output. Then we can go back to the rest of the function, right? But with the interrupt, we can like jump out and finish the interrupt, go back. Okay, so here's the differences. Okay, and here more like showing the transfer of control for the interrupt. So if we have the user program, like stuff I'm to do the stuff of I, right? So once it happened, we will jump to the interrupt handler, let it finish. Once it is done, we will return back to where it occurred. Okay, I and I plus one. So and then we will continue right to finish the rest of it. So here's a transfer of it. Okay. And if you remember the base cycle, right? Okay, that we will on top of it, we see add more. Okay, start. If you finish the end here, we have to fetch the next instruction, execute, and then if you remember, we execute state will go back and fetch again right here. And right here, if we had the interval enabled, then maybe we'll check like for some interrupt or initial the interrupt handler. Okay, and then we will go to the interrupt stage and execute it and fetch state and go back. So you will see the fetch state and execute stage right here, right? And we are adding the interrupt. If we don't have interrupt, maybe we just go back right here. Okay, so you see. So on top of it, we build one more part is the interrupt handler. Okay, so we add the interrupt state. So here's the instruction cycle with the interrupt. Okay, first the basic one and the advanced part. And here's the picture. So it is no interrupt if we have to compete. And this one without the interrupt, you see the circle like referring to like 1, 4. Okay, and then we're waiting for the IO. And then you compete, and then we try to finish 5 and go back. Okay, 2, 4. Okay, and then IO 5. Okay, and then again 3. Okay, but with the IO, so you will see we are better utilized of the CPU, the processor. The reason why 1, 4, 2, 8 completed, and then you see we are waiting for IO operation. We already able to execute 2, 8, and then 5 to B 4, right? And then IO. So you see mainly is that while we are waiting for IO operation, we can execute for the next part. So you see why it looks like this. Okay. So we can better utilize the CPU. Okay, process power, and then the shown. So you will just like keep going right here, keep executing, and then we have like 1 to 4, and then execute, go back. So we are not wasting the time for processor. So here's the idea. And here will be kind of like simple intro processing or for the hardware. So when we look at the hardware part, so the device controller or some other system hardware, so they will issue an interrupt. Okay, so once you interrupt the processor finish the execution of the current instruction, first let's finish the current one, and then the processor will signal an acknowledgement of the interrupt. Okay, so they will push the PS down. Okay, and then the PC, okay, onto the control stack. So later you will see the picture with the control stack, okay, like this. And then we'll load the new PC value based on the interrupt. Because if you remember, the program counter is the address of it, right? And then we'll go to the software, maybe we set out remainder of the process stage of information. So let it know the process interrupt, and then later we will restore the process stage information, and then we can restore the old PSW and the PC, the program counter. So after we finish interrupt, we'll go back to it. Okay. So here's the hardware part is working, and then on the software part. Okay. So they're working together. And that's what we see. And here's the change of the interrupt. So right here we have the, if you remember, we talk about the control stack, right? So the control stack, and maybe we are running. So I'm just telling you, maybe assume here's the you see the number sometimes like from the bottom on the top, smaller number, higher numbers. Okay, so t minus m, m is the stack right here, m size t. So right here, and also the y is the interrupt, so start and return. Okay, surface right here, and then the user program, so start from n. Let's say we are control stack, we're going to execute the n plus 1, and then if we are the interrupt comes in, okay, and we will go to the interrupt, execute it. And after finish, we will go back. So we have the stack pointer, go back to stack pointer, and then we have some general register, like same thing. Here's will be the control stack. Okay, so here's the processor or saving. Okay, and then after we return it, so how it looks like, we have the n+1. So n+1, and then the program counter. So you see the y plus l, and n+1. The program counter when you, if you remember. And then we have the general register still the same, no change. And then the stack pointer, if we t, right, t minus m, we go back to the original. So we will return to the interrupt. So here's the path. Okay, so original t right here, the stack pointer, maybe we have a go back, store back. So here's the way, it's like we handle it. And we need to know, actually, there's not only one interrupt. Actually, in reality, the operating system have to manage multiple interrupts. Okay, so interrupts within an interrupt, more interrupt. Okay, nested interrupt is possible. Okay, but we can show you, like, if we have multiple interrupt, like let's say user program where one interrupt and then go back and then another interrupt, or like one interrupt and then we have the another high priority interrupt, then we have to transfer. So we will see right here the next one, the next interrupt, go X, and then we have another Y. Okay, complete it and return back, return back. So it's the called the next interrupt processing. So what will be here we going to cover is the interrupt. So here's the two questions you can think about it. So instead an interrupt is a mechanism so used by system modules to signal the process. Okay, that normal processing should be temporarily suspended in order to handle requests or transfer from modules, usually an IO device. True or false? Should be true, right? And then there's some like common class of interrupt is, if you remember program, yes, the program itself. Okay, trained by program timer of the processor, and then also the I/O. So all this will be the classes of interrupt, and then last one will be the, if we remember, the last one of interrupt will be right here, hardware failure, right? So there are the four classes of interrupt, and here's some it is a question right here. You can think about that. So mainly is the top, but we have a computer system. So it connects the I/O modules, control symbol, the keyboard and printer. Okay, teletype. Okay, so here's the following some register contained in the CPU, and then they will connect directly to the system bus. There's the input register, output register. Okay, the input flag, and then the output flag. Okay, and also the interrupt enable. In the beginning, let's say if we only have four register in the above, okay, right here, 1, 2, 3, 4, then how can I drive the IO with it? So suppose like we have the input flag, input register way. So normally we will like maybe we have input, so there's 1 bit. So let's say we have enable the input flag, then we can read the input register. So we can save it up with 8 bits. Okay, so save it. And then if we are ready for the output, then we will after we finish, then of course, okay, so we will disable the input flag. Okay, so it's done. And then if the output flag is enabled, okay, then we can output it to the output register and then disable it. So it's the regular way. If we have the it asking, okay, if there's an interrupt, so mainly it's the interrupt enable. So the CPU is okay, and once the interrupt enable, so we always checking the IEN. Okay, so once it's enabled, let's say we enable for the input. Okay, interrupt. So after the interrupt enable, then we enable the input flag and then with it. Okay, once it's done, disable the input flag and then done with the interrupt. Okay, so disable and with like in ready for output. So we enable the interrupt again and then put it the output flag and then we output setting to the output register. So here's the more efficient because the reason we talk about it because we are waiting for it. Just imagine without interrupt. If you remember right here, so we are need to waiting. Like we always have to go to IO and check. Okay, So we always need to check the right here. The question is like right here. So we have to check also input flag or output flag. Like, are you ready for input? Then we are wasting time. But if the interrupt enabled, that means the IN. Once it's enabled, then we can go to like check the flag. Okay, it's enabled. So it's way better than just like always going to check it. So here's the idea of it. And so far that's it for this class. And next we will continue about another topic is the memory. Okay. And don't worry about the assignment. So the next assignment should be like come back um from next week. Okay. So you don't have to worry about that. And thank you.